Hello and welcome. Today we'll be taking a trip to a black hole. This and next lecture will be what it looks like to go near a black hole and the effects that would be produced. So this is a online lecture series of 15-minute lectures being taught at Michigan Tech. We're trying to highlight the extraordinary concepts in physics, calling it Physics X. And you can see all these lectures on iTunes, or you can find them at Google here. And if you can read this, you can even go to that small address. So let's jump right into our black hole today. So first of all, we're going to be jumping only into a source-chilled black hole because it's the easiest. So let's get the easy stuff first, and that's what I know best. So this will be partly based on a paper I published called Visual Distortions Near a Neutron Star and Black Hole, which was published in the American Journal of Physics a while ago. So you can also see all of the movies published here on a web page that I've maintained since '94, I think, called Virtual Trips to Black Holes and Neutron Stars, where you can see many of the videos and even more videos than are shown here in this lecture. So this is a subject I've studied a bit. Okay, so let's talk about black holes a bit. So when you're far away from a black hole, then the acceleration due to gravity would be Newtonian and be given by the g, which is the gravitational constant, mass, which is the mass of the black hole, and your distance from the black hole squared. So in general relativity, it reduces to the same as Newtonian gravity. And when you're far away, you don't feel any gravity at all. However, when you get close to a black hole, the acceleration, although general relativity doesn't like to use fields, you would feel an acceleration toward the black hole given by this formula there, where RS is the Schwarzschild radius, which is the radius of the event horizon. So going past that, there's no return, and we'll look at that in some detail. So if you tried to orbit the black hole, then you would find that going to within at 3 Schwarzschild radius is the last stable orbit. Inside of that, no matter what you do, you're spiraling into the black hole if you have mass, a significant amount of mass. At 1.5 times the Schwarzschild radius is the photon sphere. That's where photons could orbit around the black hole. So actually, you could spin out from the last stable orbit if you've got mass. At the photon sphere, if you're a photon, you're going in orbit around the black hole. So here's your black hole, and here's the photon that goes around in circles. And actually, it's an unstable orbit, so if you were slightly outside the photon sphere, you would spiral out, and your photon will spiral out, and if you're slightly inside, you would spiral in. So at 1 times the Schwarzschild radius, that is the event horizon. Inside the event horizon, were all the mass to somehow be captured in a point, you would have the Compton radius. And if somehow it could go even further than that, which is beyond modern physics' understanding, you would have a singularity where you would just have all the mass at a point. Okay, so this is the general relativistic Schwarzschild metric, which tells people how to compute things, how to compute orbits of where you would go, what photons would do when you get near a black hole. It's given in terms of curvature effects. So this is time, including time. This is radius, and then you calculate times and distances between them. So as I said, when you go to infinity, space is flat, which means that when r becomes much larger than rs, this becomes 1, and this becomes 1, and you just are left with a flat geometry. So black holes, you might know, attract the same as normal matter. So if we were to make the sun into a black hole, then it might become uncomfortable on Earth. No one's debating that because we like the sunshine here. We're sort of addicted to it. However, the Earth would not go off on any strange orbit. The Earth would continue to orbit the sun, the black hole sun, just as it always has. So it wouldn't change any orbit. One difference between, let's draw a line here, the Schwarzschild metrics, gravity, and the universe as a whole is that the universe is not flat as you go to infinity. So however far you want to go away in the universe, you will not find, unless the universe was always flat, you will not find the curvature goes away as you go to any distance. Also, you can see these gravitational lensing effects. You can see the deflection of light near black holes with a telescope, and there are now known gravitational lenses where you can see the effects. We'll review some of those. And orbiting the black hole, looking at the outside universe, would be similar to spinning in place. Okay, so we're going to go to a black hole. We're going to step in from infinity. Now the black hole is going to appear black here, totally black. We're not going to include evaporation effects. We're going to have the black hole be relatively massive, so we don't have to worry about that. Everywhere where you see blackness is everywhere inside the photon sphere. So the photon sphere, as I said, is outside the event horizon. So when you look at a black hole from the outside, you're not really just seeing the event horizon. You're seeing where the photon sphere is, because photons that spiral in under that would. So if you were to shoot a photon at a black hole, in the event horizon it would go right in. If you shoot it at the photon sphere here, it would spiral in and hit. Therefore, since general relativity is time symmetric, photons trying to come out, well, they wouldn't actually, if they wouldn't be able to fall in. So in that case, it's not time symmetric. But you would get spiraling things that would go into the black hole. So another aspect of lensing is that surface brightness on the averages remains unchanged. So we'll see that in the future images. So when you were to look at observers falling in would appear to move slower and would appear more red to you. It would be redshifted. However, as you fall in, when you look to the outer universe, you see the outer universe as more blue, because those photons are falling into you and they're gaining gravitational energy, and they also appear faster. So if you see your twin far away, your twin would be moving unusually fast, and your twin would think that you are moving unusually slow. Okay, so here's a movie. I played it once in practice. So this is what it's like to go near a black hole. So it's real fast. So I'll try to play it with pausing here. Okay, so caught it. So here, when you're far away, oops, it's not happy. Let's minimize that. So when you're far away from the black hole, you just see a normal space cartooned here. Let me see if I can freeze it. So here we are, holding it down. This is normal space. This is actually the constellation of Orion. There's the belt of Orion. This is Sirius. This is Betelgeuse. No, actually, that's not Betelgeuse. That's another star. I think this is Betelgeuse. So as you come closer to the black hole, you then start seeing a black spot open up. So let's pull that back here. Oh, it's not happy. Okay. There we go, got it to replay. So as you go closer, it's a comedy. You see a black spot in the center, which is where the black hole opens up. And I'll practice on this so the next time I show videos, maybe we won't have these problems. Okay, the next slide. So this is the way gravitational lensing works, because what you see when you go near a black hole is strange, unusual lens effects. You see that here's Earth where we're seeing things. So here's a distant galaxy here. So the distant galaxy, here's a lens here, which could be a cluster of galaxies. Light here can take two paths to the observer from far away. So when you look at something with gravitational lensing, you can see more than one image. And sure enough, when you're going near a black hole, you can see more than one image of the distant universe here too. So we actually see these things in the universe. This is an Einstein ring, and I'll discuss that in a bit. So here you see a galaxy that is distorted into an Einstein ring here, and here's what the model says. So it looks pretty good. So here's a cartoon picture of what was going on. So this is the black hole when I mapped the surface of the Earth onto it for a slightly different case. Here is the belt of Orion, but here inside the Einstein ring here, you see another image of the belt of Orion. Here you see Sirius, but when you look inside here, you see another image of Sirius. So every time you see something, so when you're near a black hole, you don't have to turn around to see the rest of the universe. All you have to do is look toward the black hole, because there are things that would come from behind you that the black hole would pull around to you So all you have to do is look near the black hole to see the entire sky. Very unusual effect. Okay, here's another image of what it's like to orbit a black hole. So I'm going to not try to stop this one, I'll just let it play. So here you can see here is where the Einstein ring is. And there's a complete image set inside the Einstein ring, and there's a complete image of the sky outside the Einstein ring. So now there's two complete images of the entire sky at least. So this is two different image sets. You will never see, well, we'll see in the, I'll detail this in the next slide. So stars cannot cross Einstein rings because Einstein rings divide complete sets of images in the sky. So you can't go from one complete set of images to another. Let's see, the Einstein ring, let's see, angular speeds diverge at the Einstein ring. So if some star goes directly behind your head as you look at a black hole or directly behind the black hole, then it will appear to approach the Einstein ring and appear to move infinitely fast. So if you were to attribute that image to be at the distance of the Einstein ring, you would think it's moving faster than the speed of light. You can always see yourself near a black hole because light comes from you, circles the black hole, and comes back to you, so you can see yourself. All stars have at least two discernible images, one outside the Einstein ring, one inside. So the Einstein ring was discovered by Einstein, no joke. If you look really close to the, well, what would seem to be the black area, the event horizon, which is actually the photon sphere, you can actually see an infinite number of images. So there's actually more than two, but the other ones are really, really dim and really, really compacted right near the effective black part of the black hole. So as I said, distant stars appear slightly bluer and their clocks appear to run faster. Let's see, objects actually near the black hole will appear redder and their clocks will appear to run slower. So this is now circling the black hole at the photon sphere. So now we've lowered ourselves to the black hole. Instead of just looking at it from a little bit far away where there's a black spot, we've gone all the way down to the photon sphere and are now looking at it. So here we see a movie where this now is the Einstein ring. And so it looks like objects are crossing the Einstein ring going up, but that's not actually true. Objects are coming in here and zipping up. So they never cross the Einstein ring even there. It's always dark below because there are no photon paths that come to you from below. Those photon paths are confined to the black hole. Since you're outside the black hole and since no photon paths can come to you, then that's black. The whole universe is scrunched up above. So the closer you get to a black hole, the smaller the universe is scrunched up above you. Okay, so even when if you're very close to a black hole and you're here, the universe will appear scrunched up above you in a bright spot at the top, and everything else will be dark. That's the last thing you would see before you go through the event horizon of the black hole, which we will discuss in the next lecture. There are details that we can discuss. Every radius of the black hole has its own infinite set of Einstein rings. Here is a movie of what it looks like to zoom right in on the dark area. If you could increase your zoom continually, you would see, actually there are images of the galactic center because the average surface brightness should be the same as the rest of the universe. But you can see lots and lots of Einstein rings, and the more you focus your telescope on the dividing area between the dark, where it looks like it's a black hole, and the bright, which is the rest of the universe, you see more and more images of the universe just compressed right there. How strange that is. That's what it looks like as you fall into a black hole. And now we'll next time talk about what it looks like to cross the event horizon. So see you next time.